In this video, we're going to look at problems involving oblique incidence. And I actually found this figure, which I think is a much better figure than some of the ones in your textbook, because I really like the way it illustrates the interface between the two materials. Material 1 being on the left and material 2 being on the right. You can see the z equals 0 plane here, the plane that represents the interface of the two materials. And then what we've been referring to as the plane of incidence. So here's the wave vector k of the incident wave, and you notice that the normal to the z-plane and k of the incident wave are contained in this plane of incidence. So I really like this three-dimensional figure where they show how the oblique incident wave for perpendicular polarization works. And notice here that the incident E is perpendicular to the plane of incidence, meaning it's fully tangential to the z equals 0 plane. And remember, we always talk about polarization reference to the E vector. So in this example, the equations, or in this set of equations, I think it's very clear. In this case, E is actually polarized in the y direction, or E is, yes, polarized in the y hat direction. And then the k vector is indicated in this particular textbook. He does not use K1 and K2, he uses beta 1 and beta 2, but that's fine. It's the same thing as alpha and J beta in a lossy material with no alpha because the material is perfect conductor. So we'll just make that little change of notation to beta as opposed to K, where K here just represents the unit vector. Beta actually represents the value, the wave number. So this propagation direction dotted with or e to the minus what we've been calling jkz is now going to go to e to the minus j beta 1, which is analogous to what we've been calling k1. And then the z direction is basically x times the sine of theta incident plus z times the cosine of theta incident, or I'm sorry, the k direction, the direction of the vector. So when we express that, then we just get x1 sine theta 1 plus, or x sine theta incident plus z cosine theta incident, and that's for our incident wave. And so then when we take the cross product, in order to get h, we get e incident over eta 1, and then we have for the h incident vector, we have the minus x hat direction cosine theta I, the plus z hat direction sine theta I, and then the exponent is the same because it represents the direction of propagation. And then you can see here we also have equations written for the reflected wave and the transmitted wave. So this is a nice collection of equations that represent both the vector directions and the direction of propagation for a perpendicularly polarized wave as a function of the angles of incidence, reflection, and transmission. And of course, we remember that the angle of reflection and the angle of incidence are the same, and then the angle of incidence and the angle of transmission are related by Snell's laws. The other thing to review here, oh, and so here's a top view, and this is the view that we've been illustrating both in your textbook that I've been using as well as on the board. So this would be the two-dimensional representation looking down on this three-dimensional figure. So the other thing to discuss is the average power. So for the incident wave, the reflected wave, and the transmitted wave, you can see here that we have the incident power expressed for each of those. So, or the average power. So let's look then at an example, and we'll start with an example from this textbook, and then we'll go to an example in your textbook. So in this particular example, we have a uniform plane wave. It's traveling in air. Here's the incident wave right here. It's obliquely incident, and in this case, the interface interface is at y equals 0, and E is in the x hat direction. So the coordinates have been flipped around where z is now in this direction, and the plane of separation between material 1 and material 2 is the y equals 0 plane. So E then is perpendicular here to the plane of incident, so this is perpendicular polarization. We're given the vector direction. It's in the x-hat direction, and then we're given the expression for the direction of propagation, It's obliquely incident. We're told that the time average power is 1.4 watts per square meter. The frequency of the wave is 3 gigahertz, and the angle of incidence is roughly 58 degrees. So we're asked to find the amplitude of E. We're asked to find beta 1, which is what we've been calling K1. And we're asked to find expressions for incident H, reflected E, reflected H, and the time average power of the reflected and transmitted waves. So for polystyrene, we're told to assume that sigma is 0, epsilon relative is 2.56, and the phase velocity is equal to 1 at 3 gigahertz. I'm sorry, mu is equal to 1, so it's non-magnetic. So the first thing that we need to find out is we need to find the amplitude of E. So basically we're going to solve for all of these constants so that we can get an actual expression with numbers here. So we're not given the magnitude of the electric field, but we are given the time average power. And we know the relationship between the time average power and the electric field is that average power is 1/2 E naught squared over A to 1. So if we then substitute in for A to 1 and average power, we get that the electric field can be obtained by the square root of 2 times 377 times 1.4. So when we solve for that, we get 32.5 volts per meter. So 1.4 is our power, 1.4. The 377 is the impedance of free space or air, and then 2 comes from right here. So that gives us E sub 0. The other thing that we need to look at is we need to look at beta 1. So that's omega mu 1 epsilon 1, and mu 1 epsilon 1 are just free space or air. And so the velocity here, the phase velocity is c, speed of light. So we take our omega, which is 2 pi times 3 gigahertz. We divide by 3 times 10 to the 8th, and we get 20 pi radians per meter. So now, if we want to solve for the H field, that's basically going to be 1 over A to 1 times K cross E. Here is the vector K. Here is the unit vector E. So our H field then is basically minus E naught over A to 1 times the vectors here and then the exponent. So now just plug in some numerical values. So we plug in for E sub 0 and A to 1. We plug in for the cosine of 58 degrees, the sine of 58 degrees, and then the same up here, the cosine and sine of 58 degrees respectively. And so plugging in, and I don't remember, E0 was 32.5 volts per meter, and A to 1 is the impedance of air. So when you plug all of those in, then you basically get that in milliamps per meter. Now, in order to get the transmitted wave, or basically the reflection coefficient, we have to know the transmitted angle. And so when we solve using Snell's law for theta transmitted, then we get 32 degrees. So since the incident wave is perpendicularly polarized, we can find the reflection coefficient using the equation for the reflection coefficient. So doing that, this is the square root of, let's go back, 2.56 is epsilon 2r. And so this is the cosine of 58 degrees times 1 minus epsilon 2 times the cosine of theta transmitted over the sum of the two. Out of that, we get approximately minus 4.38. So now the electric field of the reflected wave can be written basically as the electric field of the incident wave times the reflection coefficient. And the difference will be that if we go back and look at those relationships, you can see that for the incident wave, you have a plus here. Actually, it's a minus, and the minus sign goes with both the x sine theta and the z cosine theta. Here we have a minus sign out front, but if you were to take that minus sign into the parentheses, that makes the z cosine theta part positive. So all that's saying is that it's moving in the reverse direction with regard to z. Notice that if you look here, the direction coming in, it's only the direction perpendicular to the plane of the two boundaries that reverses. The other component stays in the same direction, which in this illustration is here in this direction. So we have done a variable change, but basically what that means is for your reflected wave up here, you'll have a plus sign. So when we do that, we multiply by the reflection coefficient. What was a minus sign switches to a plus sign as illustrated here. And so there's your expression for the electric field of the reflected wave. The reflection coefficient was negative, which is what gives the negative sign here. Then the magnetic field we can obtain by 1 over A to 1 K cross E, with K given as shown. And so the K vector then gets crossed with the, or sorry, this is the result of K cross E. So we have a minus Y sine theta R plus C cosine theta R, and then the exponential. So after we plug everything in, we get a similar expression. So the time average power of the reflected wave can be found from basically this expression. When you plug in for the incident field, the reflection coefficient, the impedance of air, and the 1/2, you basically get 0.269 watts per meter squared. Now we can use the principle of conservation of power to get the time average power of the transmitted wave, because we now know the time average power of the incident wave that was given. So basically, you can use this expression right here, or a combination of this one and this one. Since we know the incident wave's average power directly, it was given in the problem, we can basically just plug that in. We can plug in the various electric fields, or since we also now know the reflected wave, then it's a direct solution to find the transmitted wave power. If you don't want to do that, then you can use this expression directly. So both of those are shown here. So this is conservation of power, showing the equations on the box to the right. This is found using the transmission coefficient and the electric field. So either way will work. All right, this is a similar example. This one is just some different things are given in the problem. So in this case, you notice we already had the expression for the incident wave. It's clear that it has a direction pointing in the y-hat direction, and the propagation direction has x and z components. So given that the direction of the field is perpendicular to the direction of propagation, and the plane that separates the material is the z equals 0 plane, so that would then mean that this wave has perpendicular polarization. So we're asked to find the polarization of the incident wave, the angle of incidence, time domain expressions for electric and magnetic fields, and for transmitted electric and magnetic fields, and then the average power density. The dielectric material to the right has epsilon r equals 4. So once again, since E points along the y direction and that's perpendicular to the plane of incidence, which would be the xz plane, and the wave is perpendicularly polarized. So the first thing we have to realize is that what's represented up here, according to the equations that we've been given both in the new material as well as in the material that's in your book, this exponent represents x sine of theta I plus z cosine of theta I, which is minus j times 3x plus 4z. So you can set the first part of the equation, k1 sine theta I equal to 3, and the second part of the equation, k1 cosine theta I is equal to 4. So you have two equations and two unknowns, and that allows you to solve for both the angle of incidence as well as k. So now that you have k, you can solve for omega using the phase velocity, and we're in air, so the phase velocity is the speed of light, and k we just solved for, so we can now find omega. So let's go back over that one more time. Basically, we're looking at what's in the exponent here, and we know that for a perpendicularly polarized wave, if we're pointing in the y-hat direction, then this exponent is x sine theta I plus z cosine theta I. So we're just drawing a one-to-one correspondence to what we're given, as well as to what the equation defines for the incident angle. And it's easier if you have a figure in front of you. So if you want to pause the video and pull out a book where you can actually look at a figure, that might be useful. Okay, so now we need to find our constants eta. So eta 1 is just eta naught, which is 377 ohms. Eta 2, we plug in our relative dielectric constant, and the square root of 4 will give us 2, and so eta 2 is 188.5. And so that then allows us to use Snell's law to solve for the angle of refraction of the transmitted wave. So when we do that, we get 17.46 degrees. Now that we have that, we're able to solve for the reflection coefficient. So once again, to just go back to the beginning, the goal here is to find the reflection and transmission coefficients so that we can get the magnitudes of the transmitted and reflected waves. We can't do that until we have the angle of incidence, the angle of transmission, eta 1 and eta 2. So that's why we've taken the procedure we've taken, is to get those angles, the etas, calculated first. So once we do that, we plug everything in, and we get minus 0.41 for the perpendicular, for the reflection coefficient. And then we can solve for the transmission coefficient by taking 1 plus that, which gives us 0.59. So now we use the relation that basically says that reflected wave is the reflection coefficient times the incident wave. So here's the reflected wave. Now let's look at how that's different. Notice first of all, in the exponent, the coefficient on the z, or the sign of the coefficient on the z, has switched. So coming back, let's look at the expression for our incident wave. So it's in the y-hat direction, it's positive. We have minus j, and we have 3x plus 4z, which means it's traveling in the forward x and forward z direction. When it hits the plane at z equals 0, the z direction of travel flips, and so it's now traveling in the negative z direction, still in the positive x. So that's the expression for E. Then H we get from the previously derived relationships, taking K cross E, and so we get this expression for H, 8.2 over eta naught, and then once again in the reflected wave, the z direction H component is also traveling in the forward direction. So plugging everything in then for H, we get the following expression for H reflected. So we've plugged in eta naught, we've plugged in cosine theta I and sine theta I into these expressions, and the 8.2, which was the amplitude of E. The minus sign also stayed with us because when we take the cross product, um, it does not flip the direction. All right, so we can get the time domain by adding the e to the j omega t and taking the real component, and basically then that means you have the vector, you have the cosine omega t, and you have the minus 3x plus 4z for the reflected wave. All right, in medium 2, the first thing we need to calculate is we need to calculate K2 or beta 2, as we saw in the previous example for medium 2. We can do that by using a ratio, or you can go all the way back and recalculate the phase velocity in medium 2 and then use K2 as omega over the phase. So either way will work. This textbook, he really likes ratios, and so he'll do a lot of his calculations with ratios like this. But you can certainly go back, calculate a phase velocity based on epsilon 2, and then using the using omega and the phase velocity, find K. So K2 turns out to be 20. We also need to calculate the angle of the transmitted wave. So we do that once again using Snell's law, and once again he's combined a few steps. I'm sorry, using Snell's law. So so that ends up being 17.46 degrees. And then we need to know what the exponent looks like. So we still have in the exponent, this is still a forward moving wave. It still has an x component and a z component to the motion. So everything stays the same, except instead of K1, we have K2. So when we substitute in K2 and we substitute in x sine of theta t and z cosine of theta t, we get the following expression by filling in everything. So that's what's going to go in the exponent. So when we put that in the exponent, we get the following expression for E. This 0.59 is the transmission coefficient, and 20 was our original amplitude. We can then determine H by, once again, taking the cross product of the propagation vector and y hat, and so we end up with this expression for H. We plug in our transmission coefficient, we plug in eta 2, and we get the end result, which we can then move to the time domain by adding back the cosine omega t part and taking it out of phasor notation and putting it into time domain notation. So we can now find the time average power of the transmitted wave by using the formula magnitude of the transmitted wave squared over 2 eta naught, which then we end up with 0.36 watts per meter. So those are some examples of how to work with oblique angles of incidence for perpendicular polarization, which is a bit more straightforward than parallel polarization.